Unit 24, Examining and Testing Welds. The broad area of quality control includes methods to improve and maintain product quality. Figure 24-1. It is one of the most important segments of industry. Another purpose of quality control is to help reduce costs. It is also an important way to maintain product safety. Quality control plays a vital role in improving in the competitive position of the manufacturer, which improves the chances for continued employment for the employees. Various welding codes used in the United States require the use of non-destructive examination to protect the health and safety of employees and people working and living near and potential dangerous industrial processes and equipment. A welding code is a document that specifies how a part or product should be designed, constructed, repaired, and tested. A few of the most common welding codes include American Society of Mechanical Engineers, ASME, Boiler and Pressure Vessel Code, and the American Weld Society Structural Steel Code. Basic classifications of quality control techniques. Quality control techniques fall into two basic classifications, destructive and non-destructive. With destructive examination, the part is destroyed during the examination program. With non-destructive examination, the examination is done in such a manner that the usefulness of the part is not impaired. Destructive examination. Destructive examination is costly and time-consuming. The specimen is selected at random from a given number of pieces. Statistically, the results indicate the characteristics of the remaining undestroyed, unexamined pieces. It does not give complete assurance of perfection because of a considerable number of defective parts could go undetected. Guided bend test. Various metallurgical and strength tests are destructive. A very common destructive test used for both weld and welder testing is the guided bend test. This test is used to qualify welding procedures and to qualify welders for code welding. The test uses a standard joint design that is welded using one of the welding processes. Generally, 3/4 of an inch to 1.5 inch wide specimens are cut from the weld meant for testing. Three types of guided bend tests are used depending on the thickness of the specimen. The face bend, the root bend tests are used for material thickness of up to 0.375 inches. For material thickness over 3.75, the specimens are machined down to the thickness of 0.375 and a side bend is used. Once prepared by machining, the specimen is pressed into a standard fixture until bent into a U shape or until it breaks. If the sample does not break, it is visually examined after bending for discontinuities, cracks, or defects. The sample passes the bend test if no cracks are larger than code allows. Figure 24-2 shows a weld specimen being pressed into a guided bend fixture. Specimens are examined for cracks and defects after undergoing a guided bend test. Tensile test. Another destructive test is the tensile test, which applies a pulling load until the sample breaks. Tensile strength is used to compare welding filler metals. Tensile strength is the measurement of the material's ability to withstand being pulled apart along a single axis. For a E7018 electrode, the minimum ultimate tensile strength is 70,000 pounds per square inch. Figure 24-3 shows a tensile test for a welded A36 structural steel plate. The machine used in the test pulls on each end of the sample until it stretches and breaks into two pieces. The maximum force applied to break the sample is recorded. Material tensile strength is tested when forces are applied to pull and break it into two pieces. The maximum force applied to the break is recorded. Non-destructive examination. Non-destructive examination is commonly used as a basic tool for the welding industry. It is well adapted to examining products where the performance of each part is critical. Each weld can be examined individually or as part of the completed assembly. Basic non-destructive examination symbols. Basic non-destructive examination symbols approved by American Weld Society are as follows: acoustic emissions tests, electromagnetic testing, leak testing, magnetic particle testing, neuron radiographic testing, liquid penetrant testing, dye penetrant testing, fluorescent penetrant testing, proof testing, radiographic testing, ultrasonic testing, visual testing. Elements of the examination symbol. An examination symbol, similar to the welding symbol, is used to indicate which required non-destructive test is to be performed. Figure 24-4 summarizes the organization of an examination symbol. Location significance of arrow. The arrow connects the reference line to the weld meant to be examined. The arrow side of the joint is the side of the welded joint to which the arrow points. The side opposite of the arrow side is considered the other side. Location of the examination symbol. If the examination symbol is placed on the arrow side of the reference line toward the reader, the examination is to be made on the arrow side of the joint. Figure 24-5. An examination to be made on the other side is indicated in the welding symbol placed on the other side away from the reader on the reference line 24-6. Examinations to be on both sides the welded joint are indicated by examination symbols on both sides of the reference line 24-7. The examination symbol is centered on the reference line when the examination has no arrow or other side significance. Figure 24-8 gives some examples. Direction of radiation. The direction of radiation is specified by symbol located on the drawing at the desired angle of the examinations. It is in conjunction with the radiographic and neutron radiographic examination symbols. Figure 24-9. Note the radiation symbol or star and how direction of radiation is specified. Combination of non-destructive examinations symbols and welding symbols. Non-destructive examination symbols and welding symbols may be combined on a print. Two simple examples are illustrated on 24-10. Examination symbols are often used together with weld symbols on multiple reference lines. Specified length of section to be examined. At times, a specific section of a welded joint must be examined. Dimension lines indicate the exact location and length of the examined section. Figure 24-11. When the full length of a welded joint requires examination, no dimension is shown on the examination symbol. If less than 100% of the weld is to be examined, the percentage of the length to be examined is indicated as shown in figure 24-12. A note elsewhere on the print specifies examination locations. Should random examinations be required along a weld, the number of examinations is shown in parentheses. Figure 24-13. The examine all-around symbol is used when the examination is to be made all around the joint. Appropriate dimensions locate the examination area. Figure 24-14 gives an example. Specifying a section or a plane area to be examined. Non-destructive examination of an area or part of a unit. before or after being welded is specified by enclosing the area with a series of straight broken lines having a circle at each change of direction. The symbol specifying the kind of examination is also shown in figure 24-15. The examination area may or may not be located by those dimensions. Use this technique for indicating a specific area for non-destructive examination before or after making welds. Major non-destructive examination methods. Although the list of non-destructive methods is fairly lengthy, 5 methods commonly used are discussed in the following sections. The type of method used depends on the various factors: type of material tested, whether both surfaces of the joint are accessible, method required by code, if the discontinuities or flaws are at the surface or subsurface of the weld. Visual testing. The most common non-destructive testing method is visual testing. Figure 24-16, a well-trained and experienced welding inspector can determine whether the weld is made to the specified print size, is in the correct location, and if there are visual surface discontinuities. Visual testing requires less time than any other inspection technique, and when used during the process of fabricating, visual testing can catch errors at each step of the fabrication. For other non-destructive inspection techniques, the inspector must interpret various indications present. An indication tells the inspector where something present is in the weld. The training, experience, and judgment of the inspector are required to determine if the indication is harmful to the weld. Although other equipment might be used, the inspector commonly uses a pocket, magnifier, fillet gauge, mirror, square, protractor, and welding standards and codes during a visual inspection. Magnetic particle testing. Magnetic particle testing is a non-destructive testing method used to detect surface and slight subsurface discontinuities in ferromagnetic metals. The process is commonly used to detect cracks, porosity, a lack of fusion, inclusions, and other flaws too fine to be seen by the naked eye. Figure 24-17. The magnetic field in the part being inspected is established, and magnetic particles, colored iron fillings, are applied to the surface of the part during this testing method. Visual inspection determines the presence of discontinuities. Equipment required for the process includes a magnetic yoke, figure 24-19, or magnetic prods, magnetic particle powder, and a power supply for the magnetic field. The magnetic field may be developed with alternating current or direct current. The magnetic particles are available in various colors to contrast with the color of the part, known as the dry method, or the particles may be suspended in a liquid, known as the wet method. Another modification is adding fluorescence to the particles. Then ultraviolet light shows formations of the particles around any defect. The inspection method uses magnetic flux leakage as a principle of operation. Figure 24-20 shows how the magnetic lines of flux are changed by the crack in the part. The particles surround the crack and show as an indication. Liquid penetrant testing. Liquid penetrant testing is a sensitive testing method used to find discontinuities open to the surface of the part. The testing method is capable of finding cracks, porosity, and other small discontinuities in most cleaning materials. To use this inspection method, the surface must be clean and free of any loose rust, oil, or other surface material. The inspector coats the part with a dye penetrant or penetrating liquid and allows it time called dwell to seep into any discontinuities. Figure 24-21A. Once the dwell time is complete, the inspector thoroughly removes the excess penetrant and allows applies a developer. The developer is usually a white powder that draws some of the penetrant out of its discontinuities. The contrast between the developer and the penetrant shows the flaw vividly. Vividly. The dye penetrant process is relatively inexpensive and easy to use. To provide more sensitivity, the penetrant may be fluorescent or require an ultraviolet light for inspection of any surface flaws. Radiographic testing. Radiographic testing is a film exposure method that uses gamma rays or X-rays to detect internal discontinuities. The radiographic testing method is slower and more expensive than methods of non-destructive testing already described. However, the process can detect subsurface flaws and provide a permanent record of the inspection. The permanent record is useful for comparison to future radiographs after the weldment has been in service. Gamma rays emitted by radioactive element and X-rays produced by using electricity pass through the materials to expose film placed on the opposite side of the part. The weld discontinuities generally show on the exposed film as darker areas because the discontinuities are less dense than the material being tested. A trained or certified radiographic technician must interpret the indications. Overexposure to radiation from the testing method is a safety concern. Proper training and use of exposure badges are required by anyone working with radiographic equipment. Ultrasonic testing. Ultrasonic testing uses ultrasonic sound wave energy to penetrate into the material and detect flaws. Mechanical vibrations in wave form at frequencies above the range of a human hearing produce the ultrasonic energy. An electronic device called a transducer is placed on the surface of the test part to transmit the waves. In pulse echo testing, the transducer is used as a transmitter and receiver of the reflective energy. Thorough inspection transmits sound waves through a transducer, and a second transducer picks up the signal at the other end of the piece. Ultrasonic waves are reflected from the discontinuities in the weld or base metal as well as the opposite surface of the part and are displayed on a video screen. Subsurface discontinuities perpendicular to the ultrasonic energy are easily detected. However, depending on the shape, location, and part geometry, the ultrasonic energy may be scattered and weak signal returned to the transducer. The ultrasonic instrument must be calibrated before use, and the proper selection of the transducer is critical to the success of the testing process. Therefore, trained and often certified technicians must interpret the indications.